Great. Thank you. Hi, everybody. Good evening. Hope everyone's doing okay. My name is Tom Di Liberto, as was mentioned, and I am a meteorologist, climate scientist, climatologist. I always say it depends on the question that's being asked of me. For most of my friends, they consider me the weather person, so they're always asking me for the weather forecast. So to them, I'm a meteorologist. My job, I am the climate scientist for climate.gov, which is run out of the National Oceanic and Atmospheric Administration, or NOAA. I'm also the social media manager for all of the NOAA Climate handles. So if you follow them on Facebook, Instagram, or Twitter, it's me. It's a team of me. I'm the one person who's in charge of all of that. So I got my background is in science. If you want to know what my current expertise, what my area of expertise is in, it's in El Nino and La Nina. I'm one of the forecasters. In fact, tomorrow I'll be forecasting the next monthly outlook for the what's going on with La Nina, and I'll come out on Thursday. But that's my area of expertise. Although I've done a little bit of everything. I've done weather forecasting, climate forecasting, and nowadays I do a lot of communication, science communication at climate.gov. And tonight, I'm going to talk about winter in the Great Lakes. That's a big topic, right? And I'm going to talk basically what's up, like what's the outlook for winter so far in the Great Lakes? How do normal winters happen in the Great Lakes? What are some interesting features about the storms that occur across the Great Lakes? And then because I'm climate.gov and I'm a climate scientist, I will also talk about what's changing. Maybe not in that order exactly, but we'll get to it. Make sure you get all of the questions in. I would love to answer all of your questions. By the way, in case you want to get further contact with me, I realized I didn't put my email address on this. My email is just tom.diliberto@noaa.gov. So it's just that name. Get rid of the little space between the DI and the L. Just one word there. tom.diliberto@noaa.gov is my work email. More than happy to also answer any follow-up questions. So let's talk about this. Overview. That's, you know what? We're going to go over all this. Basically, I want to talk about how climate science is bigger than just global warming and climate change, but it's happening. Humans are warming our world, and we're doing things that are making certain extreme weather events or outcomes occur more often. Some occur less often. I'll go into historical observations, the cause of global warming, why we know it's happening, some future projections focusing on the Great Lakes in particular. I'll talk about some of the impacts they're having, what we can do about it. I'm also going to focus on, again, the local impacts and local changes, as well as just talking broadly about what climate is like in the Great Lakes. And then also give you some cool sources of some really interesting information, as well as some really handy tools that make kind of an explore at your own leisure sort of thing, where you can look at climate data and climate projections for every county in the country. So no matter where you are or what area you're looking for, you can find the most interesting or up-to-date information about what scientists are thinking, at least what the data is saying, as we move into the future. First off, let's start at the very basic thing. Right off the bat, I always like talking about what is weather, right? Now, we're looking at an image that's taken out in Arizona. And you're looking at that photo. If you don't look at the clouds, you look at that photo and you're saying, looks dry, right? There's desert-like vegetation, dusty soil. And then you look at the clouds and you're like, oh yeah, it's raining there, right? So what's weather? Weather is raining in the desert, right? If I was going to tell you, right, that's weather, a weather event. It's raining right now. I can feel it. I can see it. I can experience. That's weather. It's a weather event that's happening. That's why I say the current state of the atmosphere in a particular time and place. So what's climate? We always say weather's not climate. It's a little bit more complicated than that. We say climate's the long-term average of weather in a region. So let me just go back real quick to this image again. If I was going to ask you what the average weather would be like in this photo for the desert, if you never saw this photo, I just said to you, what do you think the weather's like in Arizona tomorrow, right? And if you weren't paying attention, you would probably think, oh, probably sunny, hot, and dry, right? That's the climate. It's almost like your preconceived notions based upon your lived experience and knowledge about what's going on of what average is without any other more information that being. That's the climate. That's why I say it's a long-term average of weather in a region. That's what we're talking about. I always say it's our weather memories. is our climate. It's what's normal, what's average. It's what we base things off of. So a weather forecast, your 5-day weather forecast is giving you exact numbers. It's going to be a high of 55 tomorrow with a low of 39 or whatever it is. If you want to put that into a climate context, you don't talk about it in terms of the total number. You talk about it in terms of how different from normal it is. So as opposed to saying 55, you'd be like, oh, it's going to be a couple degrees above average tomorrow. That's taking a weather forecast and putting it into a climate frame. And that's the difference between that. So climate change then is the changing of what that normal is. And you can see how immediately how that could be a problem, right? Because we base a lot of things on what we think is normal. Now you're changing the normal. It's basically saying that we often use our knowledge of the past to inform the future, especially as it relates to climate. But what happens if the climate's changing? It means that your past memories aren't as useful in predicting or helping you plan to do something in the future. I'll get into more about what that means to the Great Lakes a little bit later. So first, right off the bat, climate science is bigger than global warming. It's also just as causes of natural variability. And this is important to note that even without climate change, climate scientists would be needed because there's lots of things going on in our climate system that would happen with or without climate change. One of them being my favorite thing in the world, El Nino and La Nina. This is normally, these two images are normally what happens during the wintertime when there is a La Nina or an El Nino. This year, we're expecting La Nina to happen this winter for the third consecutive year. And what that generally means for the Great Lakes region, maybe the southern part of it, you're looking basically at seeing slightly wetter conditions normally during La Nina. And the reason for that is that the jet stream kind of dips into the area. Basically, the jet stream, in this case, the area fast moving wind, 30, 40,000 feet in the atmosphere, serves like a storm highway. So that highway, basically, that atmospheric highway gets kind of pointed in your direction a bit more. And that's why you tend to get a little bit wetter than average, although there's a lot of things that can happen during a year. Another thing that you may have heard of before, the polar vortex, I say with my hand shaking. So the polar vortex is also really just talking about the jet stream. The jet stream weakens occasionally. Think of it like an elastic band that kind of loses its elasticity and becomes all wobbly. That allows cold air to cycle down, really, really cold conditions. Conversely, if it's really, really strong or tight, it's really west to east, that basically keeps that cold air locked to the north, and it keeps all the warm air. It usually leads to a warmer than average winter. But this can happen. There's these cycles. It's called the Arctic oscillation, which is a pretty boring term for something, right? So it's amazing how the polar vortex has basically consumed has taken over the throne of that phrase, even though it's not exactly the polar vortex. But you can see why, because it's much more interesting than saying the Arctic oscillation. It sounds like an 80s new wave band. Polar vortex is much more interesting. And that's another thing. Natural things. These happen with or without climate change. These are natural variability that needs to be monitored, understood, and forecast, have ability to understand what this has big effects on seasonal, especially winter conditions across the entire country. So what is the latest winter outlook? Now, the new winter outlook will come out. In fact, the official announcement of the winter outlook will come out the third Thursday of this month. So we have a couple more weeks to wait for that. But this is the one from last month, looking at the December, January, February period. It looks very much like a La Nina forecast. What does that mean? Well, Tom, I say to myself, precipitation wise, you're looking at exactly that. You're looking at, generally speaking, a slight tilt in the odds towards the seasonal total precipitation being above average, while the southern tier of the United States is tilted towards dry. Temperature wise, again, the southern tier, if it's dry, it's probably warmer than average, also warmer than average, but that extends all the way up the East Coast. And then you have this area from like basically the Northwest to the North Central part of the United States, again, maybe to the far reaches of the Great Lakes region, seeing a slight tilt in the odds towards being cooler than average, or colder than average. So what does this mean for Chicago? What does it mean for Michigan? What does it mean for Wisconsin, Indiana, Ohio? Well, a lot of this doesn't necessarily mean that you're going to see guaranteed to see above average snowfall, right? You still need to be cold enough to snow. But I mean, if you want to like snow, you'd prefer to have an above average temperature forecast, above average precipitation forecast, for these things. And again, this is pretty consistent with what you'd expect to see during a La Nina winter. So let's talk about climatology for a little bit. I love snow. Snow is one of the reasons I got into the field of meteorology. I grew up on Long Island, so I love nor'easters. I love getting just pummeled with 1.5 feet of snow. I like going outside and having it like I'm going into like just a blast freezer and it's just like spitting ice at my face. I love it. And so these are something I really, really like to know. But it's interesting to me because I mainly focus on the East Coast growing up. And it's a little bit different when you look apart the central United States in terms of how snowstorms develop. These are the types. You have about 5 types of snowstorms that kind of move across the Great Lakes region. One, you can see it says up there is Alberta, your Alberta Clipper. It comes from Alberta. Usually these are quick moving, dusting of snow, not a ton amount of snow, but quick moving storms. Then you have these other ones, number 2 and 4. I want to specifically focus on are your big snowstorms. Why? Well, looking at the tracks of these, I'll explain a little bit why. But these 2 storms, we see these storms kind of forming on either in the Front Range, just on the other side of the Rockies, but also this other storm which kind of hooks through Oklahoma and Texas up to the northeast. And you can see here as the storm tracks that the Great Lakes tend to be on the west side of these storms as they move through. The reason why that's important is if the winds blow around a storm counterclockwise, the west side has more northerly winds. So that's basically meaning you're locking that cold air in place. So that precipitation falls as snow. I would probably say type 2 probably has, well, depending on the track of type 4. Type 2 here would mean this storm right here, this exact path would just pummel areas just to the west of the track, especially the closer you are to there's a sweet spot close to the center of that storm where you're basically stuck in the heaviest amount of precipitation, but also cold enough still for snow. So Alberta Clipper, let's put it in motion with my fancy graphical skills. There you go. That's basically how it works. I'll see it again. Alberta, over the area, some light snow. That's a pretty quick thing. I call this conversational snow. It's a pretty one. Get your kids out and take a family photo type of snow. It's nice. It's pretty. It might be gone in 3 days. Unlike these other ones. Now this storm, this is more your type 2 or type 4. You have this really wavy jet stream. You have cold air coming down from Canada, really warm air to the east. And in between those two, the temperature difference between these 2 air masses is what gives that storm its strength. And you have this wobbly jet stream as well. And if you're stuck in the middle of it, if you're stuck right there in the Great Lakes, you can get a very fierce snowstorm. And it's like those types of snowstorms we're looking at. Now, a lot of things have to come together for any of these storms to happen. And you can see here, this looks if I just move this to the East Coast, you got yourself a nor'easter, right? It just depends on where these things are located for why they have the names they have. They're all snowstorms, pretty much, and rainstorms for many too. Let's not forget that I live now outside Washington, D.C., so mainly I see a lot of rain. I haven't seen a lot of good snow in the last 5 years or so. That's your normal conditions for where you see snowstorms. Now, La Nina can change how often the jet stream gets into these sorts of configurations. It can make it more difficult. I like to think of it this way. Think of La Nina like the coach of a 3rd grade basketball team, right? The coach draws up these plays, but it's still a bunch of 3rd graders running the play. The 3rd graders in this case are Mother Nature and the weather, right? So La Nina can put them in the way that it's supposed to look, but there's a lot of chaos in there. That means all sorts of things can happen. And that's kind of the difference. So it's not guaranteeing something. Just because a coach drew the play doesn't mean that play is going to be run as you expect it to be, because we all know that kids can be kids when they're young, right? The same thing with our atmosphere too. Okay, basic stuff. I'm going to go over a little bit about climate change right now and then end with local changes, kind of tying it back into the beginning thing. Fun. We're warming our world at an increasingly rapid rate. It's the warmest period currently in the history of modern civilization, going back quite a while. For most of you, climate systems, we're now tilted towards warmer than average. This is looking at basically the changes in the last 30 years of the end of the 20th century, beginning of the 21st century compared to the beginning part of the 20th century. For the United States in general, the globe is warming completely, especially the Arctic region. But in general, you can see both winter temperatures and summer temperatures, not as much in the southeast. It's been kind of an interesting, weird little slight cooling, which might be related to poor air quality with things slightly reflecting the sun's light. So as you clean the air, ironic, it's funny enough, you'd actually make it warmer. But generally speaking, it's warmth for a lot of areas, including the Great Lakes. And what does this mean? Well, this is taking a look how another reason we don't have to look at just the average temperatures and how they're changing. Well, we can also look at just how often records are broken, either a hot record or a cold record. And in a climate that's not changing, you'd expect these numbers to be generally similar to each other. There'd be variability because, the weather is the weather, but it's clearly not. This is going back to the late 1990s, and warm records are far, far outpacing cold records. But important to note here, cold records aren't zero. You can still have cold records set in a warming climate. They'll happen far less than the warm records, but you can still see a cold record broken. And that's an important thing to note as someone who deals with questions a lot. We also like, well, it was cold yesterday, set all these records. Yeah, that's not to say that can't happen. It doesn't happen as often as the hot records, as you can see here, but it can still happen. But generally speaking, this is looking at average temperatures risen by about 2 degrees Fahrenheit since 1900. The interesting things to here is take a look at, I didn't updates for 2021, but 2014 when it happened was the warmest year on record. Every single year since 2014 has been warmer than that year. The last time globally average temperatures were below the 20th century average, which is this line, is 1976. I always made the joke back in this is now a dated joke, but I'm going to make it anyway. That's when A Star is Born starring Barbra Streisand was in the movie theaters, as opposed to the one that was Bradley Cooper and Lady Gaga. A long, long time ago, since we had temperatures below the 20th century average. And I can't imagine that unless there is a massive volcanic eruption that shoots a whole bunch of stuff into the stratosphere, that's not happening anytime soon. Why? Well, the reason for this is pretty simple. It's kind of known for hundreds of years at this point. Greenhouse gases in our atmosphere are rising, especially carbon dioxide, the most abundant of those greenhouse gases. I can tell there's some nuance there, but in general, you're looking at carbon dioxide having a really big influence on this, and it's been rising since we've been burning fossil fuels, and the rise is completely due to the human emissions of greenhouse gases. Generally speaking, this is how it breaks down from 2018. In terms of sectors, I always found this kind of interesting. Pretty even amounts between transportation, electricity is where greenhouse gases come from. Then you have a little bit less to industry, drop down to agriculture, commercial, and then residential, and how it looks. And this is where we are currently, taking a look going back 800,000 years, a partial history of our CO2 levels. We're currently 418 or something like that. I forget the exact number. We're high. Probably the highest. This only goes back 800,000 years, but more likely than not highest in at least 2 to 3 million years. And I will say this, greenhouse gases in and of themselves aren't a bad thing. Greenhouse gases keep our planet warm. Without greenhouse gases, Earth's surface temperature would be closer to 0 degrees Fahrenheit. Greenhouse gases are good. They can keep us warm. The problem is you can have too much of a good thing, right? So you can have, just because water is good for you doesn't mean you can't drown. So as we increase this, it is basically making sure there's more energy kept on our planet, which leads to a surface warming. While Earth is constantly trying to make things equal. Basically, the Earth receives the same amount of energy from the sun. It's trying to emit the same amount of energy back out into space, searching for equilibrium, because increasing greenhouse gases are keeping more in there. Temperature has to rise to see if we can make that equal. And we're currently at an imbalance between how much we are emitting less to space as we are getting from the sun. So you might be asking, how do we know this is human caused? Well, we know how hasn't climate changed in the past? It has, for a lot of reasons. A lot of the reasons are right here. We've seen changes in the sun's energy output. It's not happening now, but that can change the climate on the planet. Changes in the Earth's orbital mechanics. These are called the Milankovitch cycles. One, that the Earth's orbit around the sun changes from more oval to circular. That changes the amount of energy we receive from the sun as a planet. Climate changes. The Earth, it's tilted in space. The degree of that tilt can change over 41,000 years. It's called the obliquity. That changes the amount of energy Earth receives from the sun, and it changed our climate. And then you have precession. So Earth wobbles. That wobble can shift. It's called the precession, 21,000 year cycle on or about. Also, as you guessed it, changes the amount of energy we receive from the sun. All these things are really well known. We can tie them back to a lot of Earth's changes in the past, as well as things like increased volcanism or other sorts of issues that are, that we can kind of tie back for how things are going. But it's not happening now. We know that the sun is not changing its energy. Those cycles are happening at way too slow of a path. If anything, our volcanic influences has not been nearly enough to lead to any sort of massive climate shifts over the last 150 years, really. And we know that the greenhouse gas rise in our atmosphere is due to carbon dioxide, because when you burn fossil fuels, they emit a certain isotope of carbon into our atmosphere, like a fingerprint. I always say it'd be like the most boring Law of Order episode ever, because it'd start and you're at the crime scene, and then the person who did it be like, I did it, here's all my fingerprints. That's pretty much what it is in our atmosphere too. So when we take a look at projections into the future, you might be curious about this. One thing we don't know, and I always say, I have a 6-year-old and a 4-year-old. I can't tell what they're going to do next 10 minutes, let alone what humans are going to do in the next century, right? So the way we look at this into the future, we have these projections or these scenarios where we have different levels of greenhouse gases going into the future based upon things humans do. The idea being that all of them are wrong, because there's no way we can predict what humans are going to do, right? We can't predict that. But the idea being is that hopefully reality is somewhere within these lines, so that you can have an idea what's going on. And each of these lines can lead to different temperature shifts. These are looking at temperatures there in the bottom here from all of these scenarios. That very high scenario has the highest amount of warming, over 4 degrees Celsius. It's like, 8-9-ish degrees Fahrenheit. And you can see how it all shifts. The key thing here is that no matter which scenario we choose, it's going to warm more so than we're seeing now. So these are impacting everyone currently. This is not a future problem. It's a current problem. Why do I say that? We often get asked, why does it matter if the average temperature goes up from like 55 to 56? It's a degree Fahrenheit. It shifts more than that in a given day. You're not just shifting the average temperature. You're shifting the whole thing. So looking at the temperature, like that's called the bell curve. It's a statistical distribution. That's basically saying that in the middle where it's highest, that's the average temperature that happens the most often, right? And then you have the extremes on either end. Climate change isn't just shifting the average temperature. It's shifting the whole distribution to the hotter side for temperatures. That means that the hottest temperatures, these events that would happen rarely in the past, have a much higher percentage chance of happening compared to current. And now you have these like tail events, these low probability events have a higher probability. You're really kind of pushing it. The Pacific Northwest heat wave is a really, really good example of that from last year. That is an event that recent studies basically take a look at and say, like, if we did not have climate change putting its finger on the scale, that would not have happened. Precipitation is a little bit different. This actually leads to there being drier conditions. Drier stays dry and wetter gets wetter. As the atmosphere can hold more moisture in it. If it rains, it can tend to rain a bit more as well. And we've actually seen observed this across the United States, looking at just the heaviest precipitation events, comparing the early part of the 20th century to the later part of the 20th century, that you've seen, a 50% increase in the number of 5-year 2-day events, like the 1 in 5 year event, basically saying like you have a 1/5 chance of seeing that event in a given year, but like 99th percentile precipitation, that's like your really, really heavy rainfall over a 24-hour period, has increased by 42% in the second part of the century, which is considerable for the Great Lakes region, Midwest as well. That's a big thing, and that's only expected to increase in the future. And we've seen $1 billion asked across the United States quadruple. Both number and cost since 1980s. This is adjusted for inflation. Now, some of this has ties to climate change. Some of this does not have ties to climate change, but it does have ties to human development. People develop things, and we continue to build things in harm's way. And when you increase the amount of extremes, or you just basically put more things in the path of the normal extremes, you can lead to there being an increase in these $1 billion events. take a look at it in terms of, where we build for in flood zones or on coastlines, or all of these sorts of things are all ways of increasing that. And more frequent events, I'll skip this. Let's go into the local changes / how does it snow? Kind of went over how did it snow before, but let's go talk about this. This is taking a look at the projected change in annual average temperature in a high-end scenario of greenhouse gases. It's a lot of greenhouse gases emitted in this scenario. I just want to give you the high end so we can get an idea what it looks like. This is temperature shifts, and the colors here, we're looking at 7.5 to 8.5 degrees. This is not going to happen, and because we know that all the projections won't exactly happen. But if you're looking at a high-end scenario, this is not it's not the most likely thing that's going to happen, right? But it could happen. Not a high likelihood, but it could happen. But this is a completely changed. The wide this is a completely changed climate across the Great Lakes. Completely changed. The average temperature shift is 7 degrees Fahrenheit in some places, higher in others. That is a very different world in terms of what the climate and what weather is like and what living is like across the Great Lakes. This is taking a look at the observed changes in intensity of the heaviest precipitation days. Looking at I hate the color bar on this because the red here means that it got wetter, which doesn't make any sense. It should be blue, right? But you can generally see here, on average, looking across the entire region, a lot of positive changes there in the intensity of those heaviest precipitation days, which could have a really big impact, especially on urban areas and suburban areas, or if you keep paving over things that absorb moisture, it runs off in the local creeks and tributaries and whatnot, can lead to localized flooding. Let's talk about snow. This is the winter talk, Tom. Let's talk about snow. Well, this is taking a look at the average annual snowfall from 1961 to 1990 compared to 1981 to 2010. And you can generally see here a northward shift in the bands of snowfall amounts, with more snowfall having been observed in the north. But generally speaking, you see those lower numbers kind of creeping up. But you have more snow in the north. What the heck does that mean? Well, when I said it rains more, or precipitation does not necessarily always mean rain. So you have increased precipitation in certain of these areas, but it's still cold enough in wintertime for it to snow, right? Because you're further enough north. So you could actually see an increased snowfall while temperatures are rising, because it's still cold enough in the wintertime for it to snow. But in the area that's still on that line, that's where you start to see that event that may have been mostly snow in the past now changing over to rain-snow mix, which is why the further south you go, you can see the decreasing amounts compared to the latest 20th century. It's a bit of a paradox, and I'll get into a little bit more in a couple of slides later. Average annual ice cover on all the Great Lakes is going down. That's not surprising. Looking at the ice cover duration, basically it's decreasing across most of the Great Lakes, and you can see the summer surface temperatures are also increasing across the Great Lakes. And the one thing I bring that up is because I went to school in upstate New York. I have family who live in Rochester, just off here of Lake Ontario in upstate New York. And I love lake effect snow. And lake effect snow, which kind of runs over the lakes that are non-ice covered, picks up moisture over the lakes and then dumps it downwind of that on parts. There's these different bands. There's some here off in the north in upper Michigan, but also gets here into parts of lower Michigan, as well as in all the other Great Lakes. The interesting thing with climate change and lake effect snow, I may have a slide in this later, but I want to mention it now anyway, because it's on my top of my head, is that if you decrease the amount of time the lake is iced over, you actually lengthen this lake effect snow season. And as long as it's cold enough for it to be snow, you can actually see an increase in lake effect snow for a period of time, even in a warming world, because those lakes actually, the ice cover is decreased. It's a weird thing to say, like, oh, climate change is causing there to be more lake effect snow. To a point. At some point, as the climate warms, it'll be too warm for that lake effect to be snow. It'll be lake effect rain, potentially, even. The lake effect snow happens due to a specific temperature difference between the air above the lake and the lake temperature. You need warm lake, cold air. that temperature difference is enough, it destabilizes the atmosphere, allowing moisture to get picked up from the warmer lake water, rise, and then fall. But fall is really powdery snow because the air is so cold. So it's a classic thing that you see after a storm passes by and you have these really cold winds coming out of the north over, let's say, a lake that has not a lot of ice over it. It picks up that moisture and then drops it. As it hits land, because land causes that air to kind of hit each other, or causes the topography, and land is not a flat lake, causes the snow to fall. But it's an interesting kind of thing that could potentially happen. And might be some influence of that, especially in the north as well, with those trends that we saw. Other things, this is more of a summer thing. I don't know why I left it in here, but I found it was pretty interesting that we actually are also seeing increases in ground level ozone in all of these scenarios. That basically is saying you have an increase in poor air quality, especially around Chicago and the surrounding areas in Illinois. And this is mainly a summertime thing. I know we're talking about winter, but I want to throw it out there too, because ozone, ground level ozone, the ozone in the stratosphere across the poles is good. That's your ozone hole. On the ground, though, is bad. It could lead to a lot of bad things in terms of your own respiratory health. So it's not something we'd like to see a lot of. Other things, if you like to plant things, we are seeing shifts in plant zones as temperature warms. So this is taking a look at that area around Chicago. Generally speaking, the previous zone was zone 5. It's currently in zone 6. This will be updated. I've been told soon, but I've been told soon for several months. There's lots of updating to go on as you go up to 1991 to 2020 soon. But again, the trend is clear that we're moving plant zones for the north as temperatures warm, specifically nighttime temperatures, which really are important when looking at plant zones. In general, looking at another thing, if you're into planting, the projected change in the days of frost, the frost-free season, basically a longer growing season, can happen across the Great Lakes. That will positively impact some crop yields through about the mid-century, but by the end, any sort of benefit to this longer growing season will be outweighed by there being more frequent, intense, severe weather. More flooding when it rains too hot, when it rains too much, and then drought risk because it gets a lot hotter in the summertime. And then more pests, just because you have warmer temperature doesn't mean the crops or the plants that grow are the plants you want them to grow. So we have more invasive species, making it more conducive for them. More pathogen, potentially plant viruses, whatnot, will also reduce crop yields. That's a general thought, currently speaking, about what that'll look like. So some tools for you all to play around with. One is the Climate Explorer. I would just Google Climate Explorer NOAA because the link is not memorizable. But this is what I was mentioning earlier. You can go here and get any data for any place in the country, for any county in the country, going out, the rest of the century, but also getting historical data. If you look curious about climate observations going back in time at a certain location, this is where you can go. If you remember that storm from back in the day, you can probably find it somewhere here on this page in your Climate Explorer. Just type in that box where you'd like to go. Here's what I took for Lake County, taking a look at projections of the number of days with the maximum temperature over 90 and the growing degree days. And you can see there's increasing trends in both of these. You can imagine this is in the 2050s projection between 1961 and 1990 for Lake County. They saw about 7.7 days with temperatures above 90 degrees Fahrenheit. By the 2050s, even in a lower emission scenario where we actually reduce greenhouse gas emissions pretty substantially, you're still looking at an increase to about 30 days. That's basically saying a month. You go from a week to a month of the summer with days above 90 degrees. That's different. That's a substantial change. But you also see this increase here in growing degree days. The temperatures basically allow your extended growing season. So some positives, some negatives, but also, again, this is a big change that has a lot of issues, especially in the summertime as it relates to heat. In the wintertime, this could potentially mean there being less snowfall or more snowfall happening as rainfall in the future. So another thing I'd also recommend going to is resilience.toolkit.gov. That's a brand new website that was put together and it's hosted by climate.gov that helps you basically get a better idea of climate risks for your county by county look of climate risks that also ties in socioeconomic data. So it'll tell you how many people, what the more facts about the vulnerable communities within that county and how many people are at risk and all sorts of information that's super useful if you're looking into kind of assessing the climate risk wherever you live. What can we do about it? Well, there are two things that we often talk about in terms of climate change. You have mitigation, adaptation. Mitigation, you're reducing greenhouse gases to, reduce the severity of climate change. Adaptation is saying, listen, great, we're going to reduce emissions of greenhouse gases, but things are going to happen and we have to deal with them now. Sea level rise is a really good example of that. It's going to happen. We should deal with that. You can think of this like it's going to rain more. We have to deal with that. You're adapting to conditions that are going to change or already changed. Two different ways. I'm not saying 100% mitigation, not good. 100% of that adaptation, not good. You have to constantly be adapting if you don't do it mitigating. If you just do mitigation, some things are going to happen anyway. So people are going to get hurt, even if you do those things. So there's a line here. Now, the exact divvying up between mitigation and adaptation is much more complex. It's much higher than my pay grade, and that's a much harder question to answer. But those are your two ways of thinking about it. Mitigation is doing things like developing new habits to avoid wasting energy, carbon-free energy sources, planting trees. It's reducing driving. It's all of land use changes are really big ones as well. You can even talk about like ways of funding, and this is all sorts of potential options that you can do to mitigate greenhouse gas emissions. Adaptation is, let's say, installing green roofs or painting a building reflective roofs or painting buildings white as opposed to dark areas to reduce urban heat island effect, or developing better stormwater management infrastructure to deal with rainfall, planting crops because it's going to get hotter, making your line more resistant, making your supply chains more resistant to there being issues. Let's say like that you're a business manager and you get a lot of things from overseas, and what if there's a concern of there being drought in that region? Is it more likely to get them to where you are? Is it increase the costs? Is there more drought making more things scarce? All of these things are things of discussing how you can make things or adapting to it. Again, free online sources, climate.gov, the Climate Resilience Toolkit. The toolkit is basically what we did to help people step through making their own community more climate resilient. It gives you a step-by-step. It also connects you with case studies, tools, experts, reports, training. If you're interested in learning more about that, that's a really good place to go. You can learn more about what's going on across the entire country. Climate.gov basically gives you all the data. It has stories, some written by me, about current climate information, climate things that are happening on, more educational material. If you're a teacher, they have a teaching climate section, all sorts of things that you can use, experiments, demos, interactives, more resources and tools and opportunities as well. And then you also have the fourth climate, National Climate Assessment, climate.gov, globalchange.gov/NCA4. The next one comes out hopefully next year, like now. Hopefully it's a year from now, the fifth National Climate Assessment will come out. Then you have the IPCC report. IPCC report is that big climate report that basically synthesizes all of the latest research on climate science and says, okay, cool. What is the current thinking of climate science or the field? And this report started coming out last August, in August 2021. And now we've had 3 reports, one just on the science, one on adaptation, mitigation, vulnerable communities and impacts, and then one on just strictly mitigation. And then also for your area, you might be interested in this one. This is the Climate Action Plan for the Chicago region. It's not for the city itself. This is for the communities around Chicago. In 2021, this came out. You can look it up at the mayorscaucus.org/climate change. This is done in coordination with us at NOAA, as well as a whole bunch of other folks taking a look at how to make the region around Chicago more climate resilient. There's a lot of really fascinating stuff in there that might be of interest to folks. The idea behind this is that we know that there are a lot of communities who want to make a plan up to deal with climate change, but they may not have the resource to be able to do that. This is taking getting all of those communities to work together to create one plan for everybody who lives, let's say, outside these major cities. Chicago probably has enough funds to be able to do their own climate action plan, but the other communities not necessarily don't. And this is where we stepped in and helped out as best we could to help come up with this plan. This plan was released to much fanfare last August in 2021. So I highly recommend taking a look at that as well. But I will stop there. I'll stop sharing my screen unless people want to bring up a slide. And I would love to hear all of you if anyone has any question. I think there are some Q&As in there.